All right, and it's kind of along, if when you're thinking in terms of partial derivatives, you kind of get the same idea. It's the same feel when you're dealing with multiple integrations as it is for partial derivatives, where you kind of look at it and say, oh, I'm just holding one variable constant. Well, that sounds great. That's not bad. So why is this so difficult? It's because of it's very easy to lose track of what's variable and what's constant, right? So and when that happens, as you've seen, catastrophe, right? So let's explore those catastrophic situations together. So we're going to learn the technique of partial integration. It's very easy to start, but and it is all dependent on whatever the variable of integration is, right? So in this case, we're looking at the variable of integration being y, so we're going to hold x constant. All right, so x is treated as some sort of constant. So, and you know, I'll just kind of pick an example off the side here. I'm just going to throw one off the side. Let's say you had something like 2 plus x squared dx. Just a quick example from like early Calc 2, maybe most likely towards the end of Calc 1. What you would do if you wanted to find the antiderivative of this is you'd really just look at it and say, well, I'm just going to slap an x onto the 2 and say 2x. But really you didn't. It was the reverse of the power rule. It's just you wanted a shortcut. You didn't want to have to do it every time. But really it was the same as saying, well, this is really 2x to the 0th, increase the power by 1, divide by the new power. And then you would do the same thing for the other piece, and that would become plus 1/3 x cubed. But then you had to remember that there was a constant of integration thrown on at the end. And that was fine. Took a little getting used to because you were so accustomed to taking derivatives. So going the other way is like sometimes maybe you subtracted from the exponent instead of adding accidentally because it just force of habit. But you understood the concept. You don't get to this class without having at least understood those basic ideas, right? So what we're doing here is the same idea, except where we had that 2 as a naked constant, it's really now 2x that is the naked constant, right? So what I want to do here is look at this expression as 2x. We got plus the y squared. I'm going to leave a little space. And then I got the d end as dy, sorry, as basically the bookend. All right. Now, because the variable in question here is a y, that tells me that everything is getting integrated with respect to y. All right. The y squared, the standalone y squared, is not going to be a problem. But that 2x, you know, a little bit of thinking has to go into play here. All right. So what I'm going to do, aside from getting rid of all this stuff because I'm getting distracted by it, I'm going to slap a y to the 0th onto that bad boy, right? Because that 2x is acting like a constant. It's not really going to act any differently than the 2 did in that little side example that I just created, right? So what I'm going to do is I'm going to increase my exponent by 1, all right? So that 0 is going to become a 1. So y to the first power. I'm going to divide this by that new exponent, so no change there. It's going to stay as a 2x. But now I have 2x y to the first, or 2xy. All right, I'm just going to get rid of that 1 because I don't need it. Then the y squared is going to, again, increase the exponent by 1, becomes y to the 3rd. Divide by that new exponent, 1/3. Got that little plus sign in there. But I need to have a plus c at the end. But the issue here is there's a little bit more to the plus c. All right, it's not just some numerical constant. if I take the derivative and that derivative involves an x only, then if I'm taking the derivative with respect to y, then that derivative would go to 0, right? So I don't want to say c, I want to say c of x, right? Because it could actually be an entire function of x. So for example, you might have something like 2xy plus 1/3 y cubed plus x squared, keeping it simple, all right? If I were to take the derivative of that, partial derivative of that with respect to y, just like we did here, that would go to 2x plus y squared plus 0, because this does not have a y in it, all right? So that's one possible result. I mean, it could have just been a 2, you know, instead of, it might have been just a regular constant. It could have just been a 2, it could have been a 10, it could have been a pi, it could have been an e, but it could also be like an x sine x minus the natural log of x, you know, so it could be a whole lot of other things going on, right? And we have to account for all of those things. So instead of writing plus c at the end, we're going to say plus c of x, all right? And I can tell you that I'm gonna put a multiple choice question on the test. And one of those choices is going to have a plus c. And maybe another choice will have a plus c of x, plus c of y, and another one will have just a, you know, an expression that doesn't have a plus c at all in any capacity. And the whole point behind that question would be for you to determine which form of integration constant is appropriate. So just keep an eye on that kind of idea, because it's really important, right? Now, just like in the last unit, I make these statements, these bold statements, and then I forget to follow through on them. So for a typo bonus, somebody gets the opportunity to remind me. So put integration constant multiple choice question on test. All right. That'll be the typo. It's not really a typo, as you know. All right. So number 2, same kind of structure. I mean, it's the same integrand, except now we're integrating with respect to y. I'm sorry, with respect to x. And there it is. So just kind of going the other way. So I'd look at this and say, this part's fine. Antiderivative of 2x is x squared. That's old school. Now I want the antiderivative of y squared. All right. Now y squared I can think of as a constant. And when you take the antiderivative of a constant, you just slap the variable on there. You can think of it that way. Or I could say y squared is really the same as saying intuitively y squared times x to the 0th power. So increase your exponent by 1, x to the 1st, divide by the new exponent, and you would get y squared. Bring down that plus sign. But now any function of y would zap away through the differentiation process, right? So if I had something like a simple sine of y, derivative sine of y with respect to x would go to 0, right? So I want to have a plus c of y. All right. So those are partial integrals, which is, you know, mind-bending in and of itself. But now we have to tackle what's known as a multiple integral. So that's the integral of an integral. All right, so you might look at that and say, okay, it's like taking the antiderivative twice. Well, yeah, yes and no. You're taking the antiderivative with respect to one variable first, and then with respect to another variable. All right, so in this case, and in pretty much any case, you're working inside out. All right, so I'm looking at this guy as my first problem. All right, that's my first hurdle. Now you look at it and say, definite integral, that sounds great. I can put that in my calculator. Yeah. That sounds wonderful. You can't do that, not yet. All right, because if you did, the calculator is going to have a hard time with it. It's going to look at it and say, well, yeah, I'd love to do that for you. However, you asked me to find the definite integral with respect to y. You told me the bounds for y are from 0 to 2. We got these x's in there, and I don't know what to do with those. Right, so that's an issue. So what we can do is tackle this one by hand, at least that first layer, and then use the calculator for the remaining parts. All right, and I say parts because in this case it's a double integral, but we're going to have a triple integral in a second, and you know, the more layers to the integration, the more handwork you're going to have to do. All right, so I'm just going to tackle this part separately. So going from 0 to 2, we have xy plus x squared y cubed dy. All right, so integrate each part separately. So it's with respect to y. So anything that has an x in it is treated as constant. So increased my exponent by, so understood that power of, oh geez, I don't know why I wrote a 0 there. A 1, increase that power by 1, so y to the second, divide by the new power, so x over 2. All right. We have a power of 3 here, so increase that by 1, so y to the fourth, divide by the new power, x squared over 4. Integrate that over the interval of 0 to 2. All right. So all that's telling me to do is replace the y's with first a 2 and then a 0, fundamental theorem of calculus. All right. So it's very important that you understand or remember that this is going from y equals 0 to y equals 2. All right. So we start off with a 2. So, and actually, as it turns out, we won't even need to plug in the 0. So we're pretty good shape there. So you plug in the 2 for y in both cases. 2 squared is 4, half of which is 2. So we're talking about 2x. And then 2 to the fourth is 16 divided by 4 is equal to 4. So plus 4x squared. All right, not finished yet, but all the hard work is over. Because now that we kind of look at where we started, we took care of the innermost integrand. We integrated with respect to y over the interval of 0 to 2. Now I need to integrate the remaining expression with respect to x over the interval of 1 to 3. Now, regardless of how easy or difficult it is, you still have the support of the calculator for that. All right. So function, miscellaneous, pop it right in. All right. So is it hard to do? Of course not. You could, this is the reverse of the power rule. But the idea that you don't have to do it is what should be the selling point here. Yeah. Assuming that it wants to let me do it. All right, what did I screw up? Yeah, it did end with a, try it again. Usually a matter of just spacing. 2x plus 4x squared. Get out of there. Ay, ay, ay. That's so weird. It's like the first time this hasn't worked for me. I don't know what the problem is. I got my variables in there the right way.
Professor?
Yeah.
I put the integrand between parentheses and it worked.
And it worked.
Okay.
Thank you. That's weird, but I'm glad it at least worked. All right, so parentheses apparently is the magic touch here. All right, so I'll write it that way in my notes. So 128/3. All right. So, you know, it whatever works. If you're fine doing it by hand, do it by hand. But as you know, when you come across cases where you're dealing with like integration by parts, you know, partial fraction decomposition and stuff like that, it's like, well, enough's enough, you know. So we want the easiest way to go. Number 4 is a triple integral, and we're not at the point where we're talking about where these multiple integrals are coming from or what they mean just yet, but we will. And once we go down that rabbit hole, it'll feel like we're never coming back up. So kind of enjoy this while it lasts. Actually, no, I'm just kidding. I think the multiple integration stuff is probably the most interesting part of the course. So hopefully you'll agree about that or agree with that. Looking at this one, the innermost integrand does not contain an x in any capacity, which is great because I'm integrating with respect to x. So I have z times the sine of y multiplied by x that's my integral. There's no more complicated than that. Now that's happening over the interval of 0 to that radical. All right. We just get a takeout delivery. So I could pop in, again, this is x equals, because that was the variable of integration, x equals 0, x equals 3. X equals 3. I don't even know what I'm making stuff up now. X equals 0, x equals the square root of 4 minus z squared. If I plug in a 0, it's not going to amount to anything, but the radical 4 minus z squared most certainly will. All right, so we're going to look at z radical 4 minus z squared all times the sine of y. All right, so we've handled the innermost integral. So now we have everything else still part of the fray here. All right, so I got to handle that now. Now, there are some techniques that allow us to swap the order of integration, right? So another name for multiple integrals is iterated integration. And so the idea is that you're just repeating the concept of integration over and over again, just with different variables. So it's not like the concept of a second derivative or a third derivative, because what we're doing is we're changing the variables of integration along the way. All right, like if you were to take the second derivative, you're taking the derivative with respect to x and then the derivative with respect to x a second time. All right, this is more along the lines of second order partials, where you might switch it up and take the derivative with respect to y after having taken the derivative with respect to x. All right, so what we need to do is be mindful of the fact that sometimes the order in which a problem is presented to us might not be the most advantageous order. Right. And when I say problem being presented to us, sometimes it's not really being presented to us by anyone other than ourselves. You know, you decide that you're interested in the solution to a problem, and it kind of works itself out that you would want to integrate with respect to x, then z, then y in your initial setup. But if you can manipulate it algebraically or graphically in order to change the boundaries of integration, you might make things a little bit easier. Like in this case, if we could swap the dz with the dy, we would have a much easier integral, right? Much easier, a little easier, right? But we don't have a basis for being able to do that just yet, right? We got to learn about why we have the dx's, dy's, dz's in the orders that they are first before we can go any further with that, right? So more on that later. So I'm integrating my z variable here only, all right? So that looks like a little bit of u substitution, but it's not really complicated u substitution, right? So what I can do is I just kind of chuck it off on the side. And you'll find probably in this topic more than any other topic, the concept of multiple integrations, you'll find yourself doing a lot more scratch work than a lot of the other things that we've done in this course. All right. So I'm just saying some function f is equal to 4 minus z squared. All right. And I want to take the antiderivative of that. All right. So I'm just kind of focusing on that separately. All right. So, and actually, I don't even need the f equals, because then I start getting into worrying about that notation, you know, the antiderivative being capital F and all that. I think I got a mosquito bite. I'm not happy about this. All right. So if I let u equal 4 minus z squared, then du would be equal to negative 2z dz. All right. If I swap out the 4 minus z squared for the u, I'm almost there. Yeah, I don't need that big of a radical. Right, we're integrating with respect to z. I suppose I should throw that in there at some point, right? I need to get rid of a z dz. So I have a negative 2z dz. That's close. If I divide both sides by negative 2, so negative 1/2 du would be equal to z dz. Then I can replace these two things with this. All right, so negative 1/2 du. So negative 1/2 u to the 1/2 du. We're looking to integrate, so retroactively it's like meh, and then meh. So the antiderivative here, increase the exponent by 1, it becomes 3/2. Divide by the new exponent, so 2/3. So negative 1/3. And we're not going to worry about a plus c because we'll talk about constants. Well, in this case, definite integral. But when we're doing side work, you don't even worry about integration constants, even if they're appropriate, until much later in the process. It's kind of like integration by parts, where it's like it's sort of an intermediate step. All right. So we're looking at negative 1/3 4 minus z squared to the 3/2. All right, so that would be my indefinite integral. So I'd rewrite. I'm hanging on to the sign of y, that's a constant. Multiplied by negative 1/3 4 minus z squared to the 3/2. That's over the interval of 0 to 2. All right. Turns out in this case, the 2 is not going to amount to anything because 2 squared is 4. 4 minus 4 is 0. All right. It's when you plug in the 0, that's when you get something more meaningful. So this is the only one that's relevant. That gives you 4 under or in the power, the binomial raised to the 3/2. So the square root of 4 is 2, cubed is 8. So that would be negative 8/3 sine of y, but this is the second part of the fundamental theorem computation. So it would be something minus that, and 0 minus negative 8/3 sine of y. So it's just going to be 8/3 sine of y. Now, you get to something like this, where you're kind of looking forward to the joyful experience of saying, all right, let me put this into my calculator because now I can. And you look at it and say, well, it's actually not that hard. I can just do this by hand. But still, like, stick to your guns. You say, like, I have the right to do this in the calculator because he said so. So by golly, I'm going to do that. Remember, I learning 8/3 sine. If I remember correctly, it understands the different variables as long as you put the appropriate d whatever. So you could put the y here, but I'm kind of nervous. I'm going to do it, but I'm going to double check with an x in a minute anyway. So 5 1/3, fraction of 5 that, 16/3. All right. But like I said, I'm a worrywart when it comes to this sort of thing. 16/3. All right. I never worried enough to check my work on any of my tests, like when I was a student. I just wanted to get out of there and be done with it. I didn't think about things like consequences. But when it comes to you all, students, I want to make sure I double check because I got people depending on me. No, it's not that dramatic, but still, it's a little bit more. All right, so there's a lot more going on here than I think something along the lines of the partial derivatives, because it's almost like partial derivatives, it's like when you're done, you're done. With the Lagrange multipliers, even those problems, that really didn't have anything to do, well, I don't want to say it didn't have anything to do with derivatives, but the act of finding a derivative is just one small step in the process. Whereas here, it seems like all we're doing is integrating repeatedly. All right, so over and over and over again. All right. Number 5 is kind of a juicy problem. It's talking about the concept of continuity and a relationship that exists based off of that continuity, but it's essentially a proof. So what I'll do is I'll put a star on that one because, without you having had a chance to look at it yet, it's just going to fall on deaf ears, my solution. So I don't want to do that. So I'll ask you to try that, or consider it. Just give it some thought. If you come up with a solution, that's great. If you want to work on it, that's great. But we'll talk about that one next class. I don't want, like I said, I don't want to just give you a solution that you're just going to have to go back to later on and say, okay, now that I know a little bit more about this stuff, I have a hope of understanding. I'd rather you have a little bit of experience with it first before I go over it with you. All right, so let's hop on over to the next page. And this will be the last thing that we cover for tonight because it has to be. Double integrals in rectangular coordinates. All right, because we're going to talk about double integrals in, rectangular coordinates. Then we'll talk about double integrals in cylindrical coordinates, and then double integrals in spherical coordinates. And then we're going to do all that same stuff again, just with triple integrals. All right, so we'll get to triple integrals before we switch coordinate systems. It's really just the concept of applications, because if you look at this, you see this nice diagram that I stole from, I believe it was the OpenStax textbook, that really, I think, does a good job of illustrating the concept of volume under a surface, right? Because what we're looking for when you think about area under a curve in 2 dimensions, there were the Riemann sums, right? So if you had, like some function, arbitrary function in space, and instead of hand waving, I could just draw a quick sketch. Arbitrary function in space. I guess that would have been a fine arbitrary function, but this is the one I had in mind. And you wanted to find the area under the curve, and like that term, area under the curve. As a student, I understood it fully. It made perfect sense. But as a teacher, every time I hear it, every time I hear somebody say it, it just pisses me off, right? Because it's like area under the curve just does such a poor job of explaining what's really going on. It's area between the curve and an axis, right? So it depends on which axis it is. And I think it wasn't until people, I started teaching it for the first couple of times years ago, area under the curve. I used that, and I had to really articulate to some students. They're like, well, how is that area under? Like, it doesn't under mean like under like forever. Couldn't it go down to negative infinity? I was like, well, I really mean that you're stopping at the x-axis. And without them being rude, they were basically saying, well, why didn't you just say that? Area between the curve and the x-axis, right? So as you should know, and I believe you do, the area is determined based off of rectangles. Yeah, so you create a set of rectangles. I'll draw them kind of exaggerated over the interval. So you have these arbitrary rectangles. I overused the word arbitrary in case you didn't know, but oh, that's not my lasso tool. That's another thing I do. But really, it's not that the rectangles are arbitrary. It's that I've decided upon an arbitrary width for those rectangles. Right? And so these end up being either an overestimate or an underestimate, but some kind of estimate for the area under the curve. And what we kind of discovered back in Calc 2, I'm pretending I was in your Calc 2 class with you. We discovered that if we were to shrink the width of those rectangles, right? So we had some width that was designated as delta x, right? But if we could bring those widths closer and closer together, right? So make the rectangles infinitesimally wide, right? So instead of having a width of delta x, and you can bring it in a little bit, let me make this like a 0.25. And let me go purple for those keeping score at home. What I could do is I could get a much skinnier set of rectangles. And that skinnier set, and I'm not going to go all the way with this, but that skinnier set of rectangles would have a thickness of dx. All right, so that width, opposite sides of a rectangular congruent, that width for that rectangle is equal to dx, that infinitesimal width. So if I populated that interval from A to B, I'm not labeling the A and B, but over the interval that you have here with those rectangles that have that teensy tiny width or thickness, then I'm going to cover more of the area. So if I had really as small as could be, whatever the width of those rectangles would be, if I could get them as close to zero as possible without actually being zero, then I would get as close to infinitely many rectangles in that squeezed into that interval as possible, right? As close as I can get. And then once we figured out what the area was approaching as the number of rectangles on that interval was approaching infinity, then we got the true area, all right? So all that's happening here is that we're giving an extra dimension to this. So this is where my ability to draw comes in handy. That's dripping with sarcasm, in case anybody's wondering. So I'm giving it some depth. So now it's a three-dimensional surface. Get another axis in there, just kind of chuck it down there for some perspective. Now, if I want to find the volume under this, the volume that's contained between this surface and the XY plane, well, I can't get it done with just rectangles. Right? What I'd have to do is populate the entire interval, because the interval goes not only across left to right, but it's going inward now. All right. I'd have to populate that entire interval with rectangles going in the other direction. Five years later. Oh, we're on the wrong one. Oh, I think it started on this one. I forgot. I already lost my place here. Remove this out. Get rid of some of this extra fluff. No, that one was actually fine. All right. If you kind of squint a lot, you might be able to see what I'm going for here. But it's going to give you that kind of thickness and depth. All right, so I'll get the x-axis back there, so you can kind of see where the floor is supposed to be. All right, but that's the idea. We're going to get little cross sections, little discs that are going to get us the rest of the way. All right, so if we have basically rectangles that have thickness to them, it's kind of like when you look at a rectangle from the side and you see just a rectangle, but then when you change your perspective and you say, oh, it's like an entire block, I didn't even see that, that's really what I'm going for here, for better, for worse. All right. So that's kind of what we're up against here. And, obviously the OpenStax textbook with its tech software does a lot better job of it than I could. All right. So what we need to do is kind of graduate from just kind of looking at things two-dimensionally to get to a point where three-dimensional stuff becomes kind of the norm. All right. So what does that mean? Well, it means we got to redefine things, but it also means that we still have a basis of understanding. Integration is still integration. Fundamental theorem of calculus still applies. It's just how we apply it is going to be slightly different. All right. So all of this stuff on this page is kind of along the lines of, you know, what I'm talking about there, or kind of, I don't know, trying to get across in the form of the diagram, just the idea that we're expanding into another dimension. All right. So when we talk about a multiple integral, we're not only saying that there's a dx, but there's also going to be, back to the diagram, there's also going to be another d going along for the ride. All right. So let's say in this case, I'm just focusing on this side, you know, just this one block here. And let me just kind of darken it in so it's a little easier to see. So that's the side and that's the top, and we have the face here. What we could do is we can look down the vertical here and create opposing rectangles going in the opposite direction, or in an orthogonal direction. So whereas in 2 dimensions, we would be looking at a dx, now we're looking at maybe a dy, or in this case, it would be a dz the way I have things organized. All right. So dy or dz, depending on your orientation. All right. So that's kind of where we're going. So let's take a look at an example. And you can see here that the diagrams get a little spicy, but how we kind of view the diagram will kind of dictate how things go. So it says compute the exact volume of the solid bounded by the surface. All right, so that surface, z equals x squared plus x squared times the sine of pi y over 6. That is that big green kind of shoe looking thing. That's what that surface is. Now the R, that's a weird way of saying that it's over a square base region, right? So if I look closely, it's easier to see on, you know, digital form, but you can see that along the y-axis, we're going from 0 to 6. Along the x-axis, we're also going from 0 to 6. All right. So we're looking at a base region. I just kind of accentuated here a little bit. That is square. Specifically, I mean, we're calling it square, but it's really a rectangular region. And the reason why I'm kind of focusing on that as a distinguishing factor is we have rules when it comes to rectangular base regions as opposed to non-rectangular. Right? So if the base of a solid, so the part of the plane, the XY plane, corresponding to the volume that you're interested in finding for the solid, if that's rectangular, then the order of integration does not matter. Right? So I can integrate with respect to x first, then y, or I can integrate with respect to y first, then x. Right? The reason why that's important is 2 pages ago, it would have been a lot easier to integrate with respect to the sine function, I think it was, than it would have been to do the u substitution. But as it turned out, we didn't have a choice, right? Or at least it didn't seem like we did. Right here, we would have a choice. So we're going to do it both ways just so we can verify that it's going to work out. But we only have license to do it either way because it's a rectangular base region. Right. So what we're looking for again is the volume of the solid bounded by the surface. Right. So how do we find a volume? Well, the volume is just like the area under the curve was the integral based off of the function, you know, and that integral would give you the area between that function and the corresponding axis. Well, it's the same idea, except we're looking for volume, and we have two axes to work off of. All right. So when I want to find the volume under a surface, I'm going to find the double integral. All right. And it really doesn't matter the order until you start deciding, okay, well, what's in my wheelhouse in order to find the antiderivative? I know how to find this antiderivative, so it makes more sense to do it one way as opposed to another, right? But we're looking for the double integral of z. We could say z, or we could say f of x comma y. dy dx. Or we could say the same thing, dx dy. Knowing that z is a function of x, y. All right, so that's what we're looking for. Now, in this case, they're asking us to do it both ways. All right, so first parallel to the YZ plane with the slices parallel to the YZ plane. So first I'm going to identify where the YZ plane is. And then what we want to do is we want to get cross sections going through this solid that we know are going to be parallel to the YZ plane. Then we're going to do the same thing for the XZ plane. All right, so let's bring it in. We know where the Y plane is. I'm sorry, the Y axis is. So the Z axis is that vertical axis. I can highlight that for us. Oh, it looked great for a second. Oh, it's wonderful, and then I lose it, right? Because it blends in. I'll go. You can kind of make it out. All right. So it's hard to tell, but when I say that I'm looking at parallel to the YZ plane, well, I'm going to exaggerate the drawing here. That's my y-axis. Probably the best I can do, but I'll try again. I'm going to go with bright blue here. And here's my z-axis. All right, so this is the YZ plane. All right, that whole shebang. All right, you can shade it in if you want. It's something like this. So what I want to do is I want to get an intersection. I want to cut through that surface so that the slice is going to be parallel to that plane. All right, so I'm kind of looking through the window there. That plane serves as the window. My perspective is looking through that window. I'm looking at the surface head on, and what I want to do is I want to make a slice orthogonal to my vantage point. All right, so what that's going to do is if I were to use that blue plane as a knife, it would create, and I'll do it along the curve that, because it's nice when they have the nets here. It doesn't always play out that way, but when it does, it's really nice. So this part here, this would be a nice little slice. It'll be a slice of the surface, all right, cut by that that plane. All right, so you can color it in, make it a little bit more obvious. All right, if you're thinking of volumes of a cross section, if it feels like this is sort of similar to that, then you're kind of in the right place. All right, your mentality is. All right, so I'm going to get my my plane out of the way here because I think it's a little distracting. I'll bring it back in later on. All right, I'm going to give this some thickness. So it makes it a little bit more obvious. All right. So it's kind of like a little bit of a wedge there. All right. That thickness is going to be along the x-axis. I'm trying to keep the coloring relatively consistent. I sometimes fail with that, but that's what I'm going for here. So this is going to have a thickness of dx. I don't know why I wrote a y there. All right. So that's what a slice would look like. So the knife came down and it cut along that little strip that I created there. You know, give it a different hue. Maybe it comes out a little bit better. So this is where the slice is happening. Big butcher knife comes right down and cuts right through it. All right. So I'm looking at a definite integral that's going to definitely be with respect to x. And it's going to go over the interval of 0 to 6. It's hard to see, but it starts off at 0. I'll do that again in red. And goes to 6. All right. If I could only just figure out the area of that red face that we just came up with, then we pretty much have what we need. All right. So that's where the y comes into play, because I could look at this and say, all right, well, let me take that axis was green, I think. Yeah. Let me take arbitrary rectangles over that interval, just like a classic Riemann sum from Calc 2. I might have to hand draw. Give it a little bit of an angle for the perspective. And so if I match this up with the axis, kind of floor it out, that's going to correspond with a dy. All right. So what I'm going to do is I'm basically going to propagate from one side of this figure to the other, Calc 2 style. My angle's a little off. So all these little Riemannian rectangles, kind of looks like a normal distribution. That'll give me the area, all right, for one face. If I could find the area of one face, then that would give me that one slice of the surface, or the volume contained between the surface and the xy plane. So what I can say now is that I'm integrating over the interval of 0 to 6 my function, which I can still just call f of x comma y, with respect to y. What that'll give me is one of those single slices. So I got my one slice. I need to have infinitely many slices, and it'd be a disaster if I tried to draw it, but I need to have infinitely many slices starting at 0 and going to 6. So I'm going to have one with a width here, 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 and so on, continuing the journey. So I'm shooting up the line, hoping that I get all of the different possible slices that can consist over that could exist over the interval, right? And once I do that, I'm just kind of working my way down the line, slice after slice after slice after slice after slice. When I do that, what I would be in fact doing is integrating together all of the areas. So this is the area of a single slice, this guy right here, times dy, which gives you a volume of a slice. Then I'm integrating all of those slices together over the interval of 0 to 6 in the X direction, and what I would end up with would be the volume under the curve, right? So then, that's all well and good, but then you got to do it. The issue is, like, why are you spending so much time on this? Well, it's because the same thing that happened in Calc 2 for some of you, and it happens repeatedly. X squared sine. What people do is they just guess. They're like, okay, I don't know, is it X first or Y? I have no idea, so I'm just going to do Y first and hope that it works out. I'm trying to get across the rationale behind why the Y came first. All right. So then this part of it should be really easy because it's just a matter of integrating. And I can tell you that the next part, and I don't even have to get into the integral part of it because that's not the point of the question. The next one is really just going to be a matter of saying, all right, well, it's the other way around. It's going to be from 0 to 6, then 0 to 6, f of x comma y, dx, dy. We're switching the order of integration, but it's a question of, okay, well, why? Why are we allowed to do that? All right, because you know that it's just a matter of switching it around. It's just a question of, okay, what on earth made us think to do that? Why are we allowed to do that? So what I'll ask you to do is just try to do the sketch part of it. All right, that's all I really care about for this. And also, I gotta put this on your radar on the test. And this one I won't need a reminder for. There will be a question, and the sole purpose of the question is for you to sketch the appropriate cross section related to the double integral. All right, so you're not going to get off the hook. If you don't understand that's fine. We're gonna continue working on this. It'll take some time because the visual aspect of it is the most challenging, but you got to get it, otherwise none of this will ever make sense to you. All right, so with that in mind, I think I've kind of laid enough on you this evening. I know I have to do that word problem, the box word problem, so I'll do that. I'll do a video for that. I'll make things easier on all of us. So let me stop the recording.